This is my lab 4 on Faraday's law for Physics 2212. To begin with, in this lab, we analyze the behaviors of a magnet when dropped through an aluminum tube, practice computing values of magnetic force, magnetic field, and current, and use GlowScript as a computational model for our experiment. Some principles that are included in this lab are Newton's second and third law, fundamental principles including Ohm's law, magnetic flux, and Faraday's law. We also have our results from our lab, so the experimental time of the magnet going through the aluminum tube is 0.938 seconds, and our model time is 0.374 seconds. Our experimental data and calculations and observations. The setup for our lab used a tube of aluminum foil, and we dropped the bar magnet through with the north side facing downward. We timed the entrance and exit through the tube and used GlowScript to create experimental data given ideal circumstances. The system was the magnet in the aluminum tube, and the surroundings were everything else. Some assumptions we made in this lab were that air resistance is negligible and a bar magnet functions as a magnetic dipole. These are just our experiment stats and our setup. As you can see, our average time was 0.3984 seconds. We have also measured our inner radius, outer radius, the width of the aluminum itself, and the length of the tube, as well as took our LAB5 magnetic dipole magnitude. We created a computational model using GlowScript. First, we made our computational constants, including gravity, resistivity, and resistivity. Then we used our physical measurements that we took in the lab. We created a bar magnet visualization and numerical parameters for the simulation to create the proper magnetic dipole and field. We created the magnetic flux of the bar magnet and calculated the magnetic flux. And this is just the rest of our computational model having to do with the gravitational force and calculating the magnetic force from the tube onto the magnet, as well as the magnetic force on the magnet. This is what our graph looked like. It's important to know that our ratio of the thickness of the aluminum tube versus the radius was not ideal for this lab, so our graph may look a little bit different than what the results were to be expected, but it does follow the model, and given a wider radius, then we would have seen the slowing down and the speeding up of the magnet when in the tube. So in conclusion, we'll do our what ifs. What if the resistivity of the conductor were reduced as close as possible to 0? Well, the current will be very high because there's an inverse relationship between the resistivity of a current. So in this case, the magnet would fall very slowly. And if there was holes or slots cut into the tube, it would affect the rings of the current model. It would result in a lower quantity of current rings, and the magnet would fall faster due to the lack of surface area, which results in the lower quantity of current rings.